Okey, Assalamualaikum warahmatullahi wabarakatuh dan salam sejahtera ya, pelajar-pelajar JIF 418. So today we are going to have our second video conference. Basically, if you can recall, in our first video conference, we did talk about material, what kind of material that we are using, how are we going to classify it. So basically, if you can recall from your last web session, that there is 3 ways for us to classify our semiconductor materials. What is it? If you can just say it out. So it seems that there's no one out there, for this web conference. Seems that I'm talking alone as usual. So back to our question just now, what did you learn during the last Webex session? I hope you have gone through the recordings. So basically, the material, the semiconductor material, we can classify it according to 3 major categories. Yes, according to the atomic arrangement. According to the atomic composition. And of course, lastly, according to their band gap. So you can see that, different composition will give different kind of atomic arrangement, and each atomic arrangement will give rise to a different band gap. So where all this can help us give some idea at the micro level how the semiconductor is. But the thing is, even though if we know the atomic arrangement, the atomic composition, and the band gap, but what's the most important when we would like to make it into device is their charge carriers. As we know that when you learn in electricity, while you are in your matriculation or in your secondary school or at Polytechnic, you have learned that, the carriers for electricity is electron. But is it true for the case of semiconductor? Is there only one type of charge carriers, or is there more? Okay, so for this Webex, our second Webex session, what we are going to talk about is from chapter 3 in your textbook, energy band and charge carriers. But the thing is, as for today, as for this Webex session, we are going to talk more on about the charge carriers. So basically, what we are going to talk today is about 3 topics. What are charge carriers in the semiconductor, which is going to answer the question that I've asked just now. And how are we going to classify the charge carriers in a semiconductor? It's very important for us to know how to classify, because not only we would like to know what are the charge carriers, but we would like to control it. Whether in a certain situation we would like them to be less, or we would like them to be more, as whatever properties that we like to have for our devices. And of course, we would like to calculate the charge carrier concentration. Okay, I mean, at least it gives us some idea whether we are going to have an avalanche or whatever it is, So basically, we start off with what kind of charge carriers and how are we going to classify it. But why is it important for us to classify these charge carriers? I mean, you didn't learn it just to memorize it, but you need to understand why the classification is important, which we are going to discuss shortly. And lastly, of course, to calculate the charge carriers as usual in physics, it's of no use we just know about the conceptual part of it, but don't know how to use it. Okay, let's start off with what are charge carriers in a semiconductor. As I told you just now, yeah, as you have learned before, yeah, charge carriers in metals are electrons. But what about charge carriers in semiconductor? Yeah, as I put down here, there's two charge carriers in semiconductor, is being electron and holes. Of course, you know what electron is from what you have learned on this slide. But what are holes? Okay, what are holes? Okay, so let's go back to our energy band diagram, our conduction band, and our valence band. You know that at 100 degrees, at 100 K, yeah, all the charge are in the valence band, where while your semiconductor is at the neutral form. So the minute where there's an increase in temperature, there is a possibility of the electron being created from electron hole pairs. Yeah? The electron is able to jump from the valence band to the conduction band, or in terms of bonding, so one electron here are being freed from the atom, yeah, from the lattice side. So now, if you look here, there is one broken bond, and here, yep, we know that our semiconductor, naturally is neutral. But now since it's missing one electron, the electron has gone to the conduction band, but what's left behind in the valence band? Of course, this is going to be an unbonded bond. So, since because the electron, you are missing the electron has jumped into conduction band. So, what's left behind will naturally be some positive vacancy, isn't it? So, if more electron, move into the conduction band, so that particular site, that particular bond, is missing here. So again, we are going to have a positive vacancy. So we can simplify that. We can conclude that holes are positively charged vacancy at the valence electron site. Because it's vacancy here. If you have learned, if you have read about defects in semiconductor, so you know what does vacancy means. Vacancy means there's a defect where something is supposed to be there at the site, but it's not there. So, the electron is supposed to be here, but it's not here. So, there's a vacancy here. So, but this vacancy, since semiconductor are neutral, so if the electron is gone, then what's left must be something positive. So that's our holes. So remember now, the charge carriers in a semiconductor are electrons and holes. Where electrons, of course, you know that it is a negatively charged particles. But whereas hole is positively charged vacancy at the valence electron site. Okay, I guess you can recall, electron transport in conduction band. So basically, they move according to the thermal excitation randomly. Remember Brownian movement? So they follow according to that random thermal movement. But what about holes? Does holes also follow such kind of transport? So how can we explain it? Okay, so let's look at this animation. Okay, so let's say one electron, get excited. So there's one broken bond. So what's going to happen is electron at some other places will jump into that vacant position to complete up the bond again. So you see that that's a missing bond here. And then the same will repeat again. So another one, move back to that vacant position and another hole is formed. So what can you say now about the hole transport? So actually, hole transport, if you look at the animation just now, is the opposite of the electron transport, isn't it? Whenever there's vacancy due to movement of electron, so another electron will jump into that position. So whenever it moves, so it will be opposite to whatever movement of the electron. Okay, look at the animation slowly when you go over the recording, then you can have some idea. Please try to internalize it rather than just looking at it without really looking at what you are supposed to look. So make sure that you can really see with your own eyes that the hole transport is essentially the opposite of the electron transport. Okay, so now you know what are the charge carriers in semiconductor, where it's being electrons and holes are positive vacancy, but electron is positively charged particles, negatively charged particles. So actually holes are not positively charged particles. It's just a positively charged vacancy. So please remember, it's not positron, it is holes, vacancy. And then, how are we going to classify the charge carriers in a semiconductor? Okay, so we know that the charge carriers are electrons and also holes. And of course, you know that there are two types of semiconductor, intrinsic and also extrinsic. What are intrinsic semiconductor? And what are extrinsic semiconductor? So intrinsic semiconductor are pure semiconductor without any defect. Whereas extrinsic semiconductor are semiconductor that has been doped. Remember, how are a semiconductor being doped? You know that doping occurs when another element replace the lattice side of the host atom, but there can also be an extra electron or extra hole, isn't it? So, intrinsic semiconductor, electron. So, and you know that, in extrinsic semiconductor, there's two types, the N type and the P type. Of course, the N type, you know that is rich in electron, whereas the P type is rich in holes. So you must know, why is it P type and why is it N type? Okay, let's go back to our how are we going to classify our charge carriers. So electron in an intrinsic semiconductor are the intrinsic carriers because it belongs to the semiconductor itself. So intrinsic means belonging to the host itself. And so does holes. Holes is an intrinsic semiconductor being the intrinsic carriers. The carriers that comes from the host of the semiconductor. Now let's see for extrinsic semiconductor. We know that for extrinsic semiconductor, that's the dopant, and that is the host material of the semiconductor. So now let's say, electron in an n-type semiconductor, where does it come from? Okay, where does it come from for the n-type semiconductor? Of course, we know that there is electron that comes from the host material of the semiconductor itself. So it must be the intrinsic carriers then. But we know that electrons are the majority carriers. But where else do we get electron for n-type extrinsic semiconductor that will make it become a majority carrier? I mean, more than holes. So you know that, if you can recall, for n-type semiconductor, we have a dopant that will introduce more electron, isn't it? So you are going to have an extrinsic carriers that comes from your dopant. Basically, when you make devices, you are going to control the amount of extrinsic carriers. But it's very difficult to control the intrinsic carriers, which I will going to explain to you shortly. Okay, now we go back to holes. We know that in an n-type semiconductor, holes are the majority carrier. Holes are the minority carrier. But the thing is, where does this minority carrier comes from? So since we know that this is n-type semiconductor, where the dopant are usually the ones that are going to give electrons, but not holes. So our holes are basically the intrinsic carriers. Now, if you use a similar argument, now let's look at the p-type. So for electron, in a p-type semiconductor, where does it come from? So we know that dopant in a p-type semiconductor only gives holes, isn't it? So electron must come from the intrinsic carriers. Okay, and we know that electron in a p-type are the minority carriers. And of course, p-type, the holes are the majority carriers. But where does these majority carriers come from? Now, of course, we know that the semiconductor has electron and holes as its carriers. So some of it must come through intrinsic carriers. And of course, since we are putting dopant into it, so part of the holes are being the extrinsic carriers that comes through doping. So now you know where is the source of our carriers in our semiconductor. That's why it's very important for us to classify the charge carriers. Because first, we know where does it come from. And second, actually the concentration of the charge carriers in a semiconductor can change according to temperature. So if you look here in my diagram, you can see that at 0 Kelvin, let's say we have dopant, the n-type dopant, and we have our electrons here at the energy level near the edge of the conduction band. But the thing is, at 0 Kelvin, there's a freeze out where the electron is at the respective energy level. It's not going anywhere because it don't have any energy. So now, but if at low temperature, some of the electron at this donor level be able to jump to the conduction band. So what is left behind are holes here. So we are going to have our extrinsic region. You see now? Yeah, at low temperature. So the electrons at the energy level near the conduction band has sufficient energy because the energy difference is small. So they just absorb the energy and just move to the conduction band. So we are going to have a lot of charge, charge carriers in the intrinsic region due to the extrinsic carriers. Yeah, only a few from this at the valence band from the host atom. So from the host semiconductor. So these are the charge carriers from the host semiconductor. But over here are the charge carriers from the dopant. So basically at low temperature, most of your carriers comes from the extrinsic level here. Okay, it's moderate temperature. Yeah, at around this area 400, you can see that some of the electrons at the valence band are able to get sufficient energy to jump, but at a very, very high temperature, so it's being dominated by the electron in the valence band. So it's dominant because they have sufficient energy now to move to the conduction band. But the one before, most of it at the dopant level has already been ionized. So now at high level only they have sufficient energy to go across this band gap. So at high energy, there is an avalanche. If you look here, a very high sudden increase in the number of charge carriers, so there's an avalanche here. So you can see that, at this particular region is the extrinsic region where most of the carriers are due to the dopant or the extrinsic carriers. But at high temperature, you are not able to control any more of the charge carriers because it comes from the intrinsic. That's why your devices, it's not advisable to put it under the hot sun because there's a possibility that the electrons in the valence band of your devices is able to go up into the conduction band, where the device cannot control it anymore. So that's why your device are able to break down if you put it under the hot sun. So it's not advisable. But now you know, if your handphone suddenly doesn't work, after you putting it on the dashboard of your car during a very hot sun, then you know why. Yeah, there must be some device that has not functioning because of a sudden flux of the intrinsic carriers in the device. Now, only at the extrinsic region that you are able to control the behavior of the carriers. So normally for our devices, we have a certain range of temperature where it will function properly. Okay, so that's why it's very important for us to know how to classify our charge according to the source, whether it's from the host or whether it's from the dopant, and avoid putting your devices under the hot sun or at a very high temperature because there's a possibility of you destroying it when the intrinsic charge carriers dominate. Okay, so I hope you get what the importance of it. Okay, please try to understand the explanation and why it's not advisable to put your device near a high temperature source. Okay, next. Yeah, how to calculate the charge carrier's concentration in a semiconductor. So knowing how to classify it, whether it's extrinsic or intrinsic, is not sufficient. Yeah, let's go back to the figures, the nitty-gritty of how to calculate it. Okay. Normally, we use the term charge carriers per unit volume, to signify it, with the small zero, meaning at equilibrium, is equal to the integration of the density of states in the energy range dE times the probability of occupancy by electron or holes, where we integrate it across the energy range dE. Okay. Density of states, is the number of energy states per unit volume. Or basically, we use our N, as a function of E as the symbol for the density of states. And the probability of occupancy, we normally use F as a function of E. Okay, so the density of states, N as a function of E, is the number of energy states per unit volume. And we know that the density is mass over volume, isn't it? So naturally, it should be per unit volume. So how are we going to visualize it? Okay, let's say we have our density of state function in the x-axis. And we have our energy at the y-axis. Let's say this is our energy at the conduction band H, EC. Where electron energy increases, as we go up the y-axis. And the density of states, and as a function of E, we can have it in this form of equation, where M star is actually the effective mass of the electron. Because why do we use effective mass? It's because this mass, because these electrons are in a crystal. It's no longer a free electron. Well, actually, it's just that we have to times a factor, a numeral factor to our mass of electron, so that it represents the effective mass. So this is the equation that for this curve. So this, if you look here, you can see that as the energy of electron increases, the number of energy states also increases, isn't it? So, number increases as the number of electron increases. Where we can see here, it starts from a less number and then it increases. And for holes, it's opposite to that of electron, where the holes energy increases as we go down, as we go towards the negative y-axis. So let's draw the curve for our energy of states, density of states, for the valence band. So this is the density of states. Now, where is being represented by this equation, where P is the mass of holes, the effective mass of holes. And if you look here again, so it's about the same as the electron energy, where the density of states increases with the energy of the holes. The number of energy states increases, as the energy of the hole increases. But if you look here, between this the conduction band age and the valence band age, there's no energy states. Why is it so? Whenever there's no energy states means this semiconductor is an intrinsic semiconductor. If you see there's energy, if there's an energy level, okay, let me just draw it. Okay, let's say we have one energy state here. So it means that what does it mean? We have a new energy level here. So if you look at this one, so it means that our semiconductor is having donor energy level here. So it is N-type, isn't it? Okay. Now, if we have our energy states somewhere near the valence band, so we know that when there's an increase in temperature, our electron will move to this energy states, so leaving behind our holes. So, of course, we are going to have extra holes in the valence band. So, it's going to be P-type. So it's just that we just have to look at the where the energy band is, where is the extra dopant level is, and then if there's none, means it's intrinsic semiconductor. So isn't it just plain easy? Okay. So you can see what you can do conclude from here. The energy states increases. With electron energy increases, and also the energy density of states, also increases. As the energy of hole increases. Okay, now let's calculate it. Determine the silicon total energy density between the conduction band H and also EC plus KT at 300 K. So we know that the equation for the density of state, NCE is equals to 4 pi. This expression 3/2 divided by Planck constant Q, and then this square root of E minus EC. So our E is EC plus KT. EC plus KT minus EC. So we know what's left is going to be our KT. And of course, like I told you just now, that the effective mass for the electron is essentially the mass of the free electron, 9.11 times 10 to the power of negative 31 times by this factor 1.1. So you just have to add this numeral factor. Then you are going to get this effective mass for electron. And of course, the H, as I said, is Planck constant 6.63 times 10 to the power of negative 34. So if you do your calculation, and K is the Boltzmann constant, 1.38 times 10 to the power of negative 23. And your T, remember, it should be in Kelvin and not in degrees. So it's 300 Kelvin. So what are you going to get now, if between EC and plus KT? So let's just withdraw it. So let's say it's here somewhere. Yeah. So the density of states, yeah, for this particular region, yeah, is going to be 10 to the power of 19 states per cm cube. It's such a huge number, isn't it? So there's a lot of energy states. So there's a lot of energy states. So now, you have looked just now, yeah, about the density of states in the energy range where we have calculated between EC plus KT and EC, which is a lot, isn't it? So now, what about the probability of occupancy by the electron of host? How are we going to get this value? The F of E. So it is probability is essentially the number of electrons divided by the number of quantum energy states. So how many electrons is there? And then divide by the quantum energy states. So that's the probability of occupancy. So now, so where are we going to get the expression for the F of E? Okay, we know that, yeah, for our charge carriers in the semiconductor, there are many electrons. So basically, the electrical characteristic of our semiconductor comes from many electrons. So in this case, many. What does many implies to you? So the behavior of the electron, yeah, we should approximate it by what? Okay, we should use the statistical laws, yeah, to average out the electrical characteristic of many electrons. So basically, there are three types of statistics that you are able to use. Yeah, it can be the Boltzmann characteristic just now. Okay, where the particles are distinguishable and no limit to the number of particles occupying a quantum energy state. But the thing is, we know that electron is indistinguishable. So we are not able to differentiate one electron with another electron. So basically, we are not able to use the Boltzmann statistics because it violates this particular rule. Because electron is indistinguishable. So now we are left behind with the Bose-Einstein statistic and also the Fermi direct statistics. So let's see at the Bose-Einstein statistics. We say that particles are indistinguishable. Okay, that's right. Electron obeys that criteria. And Bose-Einstein also said there is no limit to the number of particles occupying a quantum energy state. But the thing is, we know that according to the Pauli exclusive principle, yeah, where you learn in the JIF 1 or 3 before that, Pauli said that only one electron can occupy a quantum energy state. So if you look here again, yeah, only Fermi direct, yeah, satisfy this condition, yeah, where only one particle occupies a quantum energy state. So Bose-Einstein statistics cannot be used. We are only left behind with the Fermi direct statistics. So now, so we are using the Fermi direct probability of energy states occupied by an electron, where according to Fermi direct probability, we can write our probability F as a function of E as 1 over 1 plus E, to the power of E minus EF divided by KT. So it depends on the difference of energy, that E minus EF, and we know that KT is also as a function of energy. And holes, of course, since we know that it's just the opposite of it, so we just 1 minus F of E. Normally, I mean, to make things easy, we just calculate for electron and then we just 1 minus the value to get the probability for holes. Okay, now let's calculate this, determine the probability of an electron occupying an energy state at Fermi level. So our E here now is going to be E sub F. So what is the probability now? So E minus EF, of course, this value is going to be 0. E to the power of 0 is 1, isn't it? So E to the power of 0 is 1, so we get half. So the probability of an electron occupying an energy state at Fermi level is half. So EF, okay, so the probability half and 1. So at Fermi level, the probability is half. Okay, so that's how you draw up the curve. Where at Fermi level, the probability is half. And when E is, let's say, 0 over here, so the probability of electron occupying, at a very, very low energy level is 1. Because all the electrons are still there. And the probability of electron occupying at the energy level much, much higher than EF, is very small. Okay, so it says that you just use this equation to get the probability where this one is being replaced by the energy level that you want. Okay. So now what happens, to the probability of electron occupying an energy level, if there is any change in the temperature? Because just now we know that, the number, the concentration of the charge carriers do increase with temperature. So what about the probability of electron occupying an energy level? Does it change also with temperature? Okay, let's see. Okay. You see here now, if at 0 temperature, if at 0 K, so E KT is equal to 0. If E, in this particular region, so E is very high, minus E, minus this value, so we get a positive value. Positive value divide by 0, so we get infinity. So the E to the power of infinity, we have this whole denominator is equals to infinity. So 1 over infinity, so is 0. So we don't have any probability of having our electron in this region. But if our energy level is below our EF, so it's a negative value. Negative divide by 0, So we get e to the power of 0. So e to the power of 0 is 1. So the probability of the energy level below our EF is of electron occupying it will be 1. But the thing is, if we have an increase in temperature, so what is going to happen? So you can see now, let's say for this energy level below the edge of the valence band, you can see that there's a probability of not occupied by an electron. See? So it's not 1 anymore, but less than 1. So there's a probability of it not being occupied by electron. But if you look here, at the energy level higher than the conduction band, there is a probability of it being occupied by an electron. See, it's no longer 0 as it before, but now it's a certain value, which is very small. If we increase to a much higher temperature, so you can see that, that's a high chance of the electron not being a level here not being occupied, and this is a high chance of it being occupied. See, there's an increase in the probability, and there's a decrease in the probability of it being occupied in this region. There's increase in this particular region. So you can see now that, as the temperature increases, the probability of electron not occupying a certain level below the valence band edge is less, and also at the energy level higher than the conduction band, there is an increase in probability of it being occupied by an electron. So you can just look at this one and draw at a much larger increase in temperature. So just something like that. So you can see that, that temperature do change the probability of an energy level being occupied by an electron or a hole. Okay, now, for cases, our energy level minus our Fermi much greater than KT, or if it's being visualized here, being shown here, or to make it simple, E minus EF is greater than KT. Our energy level here minus the EF is greater than K 3 times our KT. So it's possible for us to approximate this Fermi direct probability into something similar. So we are using the binomial approximation, or its name is Boltzmann approximation of the Fermi direct probability function, which essentially, if you look at the binomial expansion of this whole expression, you just take this part of it, the first part of it. So it's just an approximation, but it's, you are allowed to do it. So instead of this difficult equation, you are able to use this simpler one. So calculate the probability of an electron and energy state at the edge of the conduction band at 300 K being occupied by an electron if the Fermi level is 0.25 eV below the conduction band edge. So what's the probability? So just straightforward. We know that 0.25 EV is much greater than our 3 KT, and we know that KT at 300 K is 0.0259. So definitely. So we are able to use the Boltzmann approximation. So we just use the equation just now. We plug in our EC minus EF, 0.25, and our KT at 300 K is 0.0259, which I guess by now you can just recall it that KT at 300K is 0.259. So it's easy. You don't have to do any calculation and just write it down. Yeah. So if you punch in your calculator, of course, you can get this value. And the magnitude is -5, which is a very, very small value. So you see here that if you draw the line, it's a very small value. Perhaps somewhere here. Yeah. Okay. It's very small. Huh? It's a very small value, yeah, -5. Recall just now that our density of states is very large, but our probability is very small. Just now is 10 to the power of 19, the magnitude, but now it's 10 to the power of 5. And if you can recall, the concentration of charge is the product of those two expressions. So yes, so the density of states and the probability, so it's a product of these two functions. So for electron, to make things simple rather than this whole integration expression, for electron we can write N0 is this expression and our Boltzmann Fermi-Dirac approximation. So in order to get this where this expression is called the effective density of states at the electron at the conduction band H. So you can replace this integration expression with this simple. You don't have to do any integration, so just do it as a product of these whole variables and our simplified probability of occupancy. So, and this one is, of course, depends on our the difference between the conduction band H and also the location of our Fermi level. Okay, before we end, let's do one calculation because that's what we are here for today, isn't it? Calculate the silicon electron concentration at 300K if the Fermi level is 0.25 eV below the conduction band H. Okay, just now we have calculated the probability, the Fermi-Dirac Boltzmann approximation probability of it, and also we have calculated the density of states. So now we just have to have it both together. Okay, so N0 is equals to NC. Okay, this is the simplified version of it. E negative EC, where you know already you have calculated it. So where you know the probability is very small and the large density of states, of course, you can get this value, which is actually to the magnitude of 10 to the power of 15. Which is essentially where our charge carriers are in our devices. And normally when we dope is about 10 to the power of 16 per cm cube. So it's comparable then. Okay. So please go over our Webex discussion, because there's no discussion, our Webex presentation. Go over it slowly and get the idea what it's all about. Okay, so basically what we have done today is identifying what are the charge carriers for our semiconductor, being holes and also electron, and also where is the source of it, and how the temperature affects it, and how are we going to calculate it, where it has two parts of it, the product of the density of states and the probability, and how are we going to get the density of states, the integration, or to make things simple, we can replace with the effective density of states, and also for and also for the probability, where how do we come from the Fermi direct, where does the Fermi direct probability comes from, and then what makes us able to simplify it to a much simpler equation, and how are we going to get those two products in order to get the concentration of our electrons at equilibrium. I've showed you just now. But the thing is, please go over to your portal. I have put there, this assignment for you. Calculate the whole concentration for silicon at 400 K if the Fermi level is 0.27 eV above the valence band age. Remember, I put here 400 K. Okay. Let me just change it to 300K so that it's easier for you to calculate it. Okay, never mind. I will change the one in the portal. So this is going to be your Webex 2 assignment. And I have set the deadline to 19th of December. So you are given 2 weeks to answer it. Please do take time to answer that one, because it will help you. It will bring bonus marks to your course marks. Okay? Kalau soalan macam ini ada marks tak for diagram? Let me see. Ada marks tak untuk energy level diagram? Soalan macam mana? Which soalan? Sorry. I didn't see that you are there, Afaf. Soalan yang mana, Afaf? Which soalan? Which question? If the question, yes, is asking for the diagram, of course, there will be marks for it. Okay, Afaf, any more questions? Okay, so we have 2 more minutes. Immediate. Okay, great, Afaf. Okay, yes. Okay, please don't forget, Afaf, answer this Webex assignment, because I'm only giving you 14 days to do it. Okay. Thank you then, Afaf. So see you in your emails then. Okay, goodbye.